All right, everybody, good morning. So before we get started, if you haven't seen, if you didn't get an email, um, the announcement from our TA, so there's two of them for the combined section. There's Josh and Aiden. I think Josh is handling the grading for section 2, so this is section 4, I think. I feel like it was like opposite what I think it is because section 2 is a little bit later throughout the day. But regardless, if you want to go to either of their office hours, that's fine. So like I said, they sent out an announcement with their office hours, and then also they've set up a Discord server. The link to join it expires in a week, so just make sure that you go ahead and join that. And what else? At the very bottom, just so it's easy and you don't have to go hunting through the announcements, I did put up clickable links for the office hours. So I've got mine until we come back in person, Monday, Wednesday, Friday, virtually 10 to 12, and then of course it'll be in person. And then the TA office hours are on Tuesday and Thursday. So Aiden's handling Tuesday, Josh is handling Thursday. They're a little bit different hours. I think they have plans. They expressed that they would want to go back to in-person office hours once we get back to campus. But for now, I've went ahead and set it up so it's virtual for throughout the rest of the semester. But if they decide that they want it in person, then I'll let you know, or they'll let you know via the announcements. Okay. Okie dokie. All right. So hopefully everybody's watched the videos 1.4 through 1.7 because it is a pretty loaded material there. But this is all determining the properties of a system and figuring out how to fix the state. Figure out if I know a handful of properties, I can figure out any other properties associated with that system. So the state principle says for a simple compressible system, the state of the system is completely specified, fixed by two independent intensive properties. All right. So
Professor, should we be able to see your screen right now?
That'd be nice. Good job, Regina. Excellent. I'm sorry. Thank you.
You're welcome.
Well, I was showing you the homepage of the Canvas site, but hopefully you can get to it yourself. But there's some buttons on the bottom, I guess, is the upshot for the office hours. Sorry about that. Thank you. All right. So compressible means that your specific volume, or the inverse of that, your density, can change appreciably. Then a sort of significance. Independent just means, if one of those properties changes, the other one doesn't necessarily change. And intensive, of course, it's not dependent on the size or the mass. Of the system. So we've got 3 different intensive properties that we've talked about so far. We've talked about temperature, pressure, and specific volume. So they're all intensive, right? So they all kind of check this box, but we need to figure out if they're independent of one another or not. As far as temperature and specific volume goes, they are always independent of one another. So the take-home message is, if you know temperature and specific volume, you're going to be able to fix your state just with that information. Same thing with pressure and specific volume. They're always independent of one another. But temperature and pressure are only independent of one another in a single phase. So only in a single phase. What that means is just in a gas phase, just in a liquid phase, just in a solid phase. what it means is that not if your substance is going through a phase change. i.e., it has multiple phases. Right, so if you've got water, for example, and we mess a lot with water in this class, we deal a lot with that. When water is boiling, you have a mixture of two phases going on. You've got liquid and you've got not solid, you've got liquid and gas. And so temperature and pressure in that case would not be enough to fix your state. All right. If you look in your book, and also if you watched the video, I think 1.4, they showed these three-dimensional pressure, temperature, specific volume graphs, yeah. But they're 3D representations of how all three of those things are related to one another for a given substance. And so a little bit difficult to actually, I guess, visualize that on a 2D page. So we often deal with just a projection. So just looking at two properties as opposed to three. So taking that 3D representation of how pressure, temperature, and specific volume are related to one another, and just looking at, say, the pressure and specific volume data, or the temperature and specific volume data. So it doesn't mean that, you know, the other information that's not on that 2D representation, that projection, it doesn't mean it's gone. It's still there, but it's just not there in a 3D format. So like I said, we're going to deal a lot with water, but this is, you know, for any substance really, has this kind of liquid vapor dome. And to the left-hand side, you've got liquid. And to the right, you've got gas. And we have a special name. So I'm going to put, if it's in a liquid phase, we call it a compressed liquid. I don't know why we add that word, but we do. So a compressed liquid, sometimes you'll see it referred to as a subcooled liquid. All different names for the same darn thing. We just like to make it more confusing. If it's in a gas phase, say it's a superheated vapor. Or just superheated. So you'll hear in Thermo, especially when we're talking about water, you'll hear us refer to it, instead of gas, you'll hear us say superheated vapor, superheated. All right, so underneath that dome, actually, let's talk about on the dome. So if I look at just this temperature, and I'm sure that we could see that. If I look at this TV diagram, everything that's kind of on this side of things, on that little line, we call it a saturated vapor. I'm going to kind of zoom in here just so I can write a little bit better. But if it's on this line, it's called a saturated liquid. And so our saturated liquid definition right here, so it's 100% liquid. But it's about to boil. Okay, but it's still, like I said, 100% liquid. You just don't see any gas bubbles yet. It's just at that tipping point. So if it's right on that line, we give it a special name, saturated liquid, but it's still a liquid. Same properties as just 100% liquid. All right. If it's right on this line right here, Shocking. We're going to call it a saturated. Saturated vapor. So not a superheated vapor, a saturated vapor. Kind of erase that, but I'll put it's a gas or a superheated vapor. Okay. All right. And so the saturated vapor kind of has a similar definition. It's 100% gas, but if we move to the left any on that TV diagram there, it'll condense. So it's about to condense. Everything that is underneath that dome, you could call it, well, it's two-phase. You could call it saturated. But it is a mixture of saturated liquid and saturated vapor. It's just a mixture of those two. And so I guess that means I can fill in this other part here. That two-phase region, or the region of saturation, includes saturated liquid and saturated vapor. Perfect. So that's our TV diagram, but we've also got a PV diagram. And the dome kind of looks, I mean, it's still a dome. It's kind of shorter and fatter. As long as I may ask you on a test to draw a PV diagram or draw a TV diagram. As long as you've got a dome there, that's all I'm looking for. Okay, so same kind of deal, right? Everything over here to the left-hand side, it's a liquid. Everything over here to the right-hand side is a gas, or oops, I'm sorry, not a saturated vapor, a superheated vapor. Go back here. Superheated vapor. And same kind of idea, right? This is our two-phase region of saturation, still a mixture of saturated vapor and saturated liquid. Okay, it just kind of looks a little bit different. All right, so it's a great line here. That's fine. All right, so on that TV diagram, remember this is all pulled from that 3D representation, and so that other data, right, on a TV diagram, you've still got pressure data, it's just not shown here, but we could if we wanted to. So if I wanted to visualize lines of constant pressure, they would look like this. Okay, so horizontal, right, flat in the middle, and then they've got these tails, right? So it goes up in the liquid region and then up again in the superheated region. So anywhere along this line, this is constant. Pressure is constant. And there are lots of those lines, right? I could draw lots of lines of constant pressure. Kind of overlapping here, but pressure is constant there. And if I called this pressure P1 and this pressure P2, they're related to one another the way that you would think they're related to one another, with P2 being larger than P1. So what you can see is, we look down here at the bottom, this kind of last takeaway message. At a given temperature, so if I just looked at, let's look at this. Maybe this is what we call T1. So this particular temperature, at that particular temperature, if your substance, say this is water, if your substance is in the two-phase region, at a given temperature, there's only one possible pressure that it could be at. right? It doesn't matter if we're over here, let's see, if we're over here on the left-hand side here or the right-hand side, it doesn't matter, right? So at a given temperature, the pressure at which the phase change occurs, phase change, right, that's our, where we have those two phases. It's called, and it's a special name, it's the saturation temperature. So this is Tsat at P1. It is the saturation temperature. So I'm going to write it actually down here. Saturation. So saturation temperature at that particular pressure. And you've got a similar idea over there with the PV diagram. The temperature didn't just go away, right? There's also lines of constant temperature, and they look similar except the tails are flipped. That's all. So right here is a line of constant temperature. We'll call this T1. Right here is a line of constant temperature. Call that T2, and the relationship between those is what you would think. T2 is bigger than T1. And so I could also define a saturation pressure. So let's call this P1, just to give it a name, but this would be the saturation pressure at T1, Psat at T1. So at a given pressure, if your substance is in that two-phase region under the dome, there's only one possible temperature that it could be at, right? And vice versa. If it's at a given temperature in that two-phase region, there's only one possible pressure that it could be at. That's the saturation pressure. So let's go look at our, let's go take a look at our tables here. So I'm on page 1 of that big PDF. And so where I'm going to be looking, I'm going to look at A2 and A3. So this is properties of saturated water, and they're just organized differently. So it's the same information that you can find in table A2 and A3. And there's also, by the way, there's an A2E and an A3E as well. But it's the same information in each of these tables. It's just organized a little bit differently. So let's go look at it. So these are properties if you're under the dome or if you're on the dome. So there we go. All right. So here we are. This is table A2, and this is for water. If you're looking at another substance, you'll have to look up the thermodynamic tables for that particular substance. This is just for water. So what we're saying is at 8 degrees Celsius, for example, this pressure right here, 0.01072 bar, that's the only possible pressure at which water could boil. That is the saturation pressure at 8 degrees. So at 8 degrees Celsius, the saturation pressure is 0.01072 bar. And I could also say at 0.01072 bar, the saturation temperature, the temperature at which that water is going to boil, is 8 degrees Celsius. Okay, so that's A2. And then if I look at table A3, like I said, it's the exact same information. It's just organized in kind of discrete intervals for pressure as opposed to temperature. So exact same information. Sometimes one of those. Oh, I'm sorry. If you have a question, please interrupt me, because it doesn't ding for me.
Hi, sorry. Yes, I have one question. Could we use these PV and TV diagrams to map out simple processes like isothermal or adiabatic expansions, or would this be trivial without making ideal gas assumptions?
So, yes, it could be used to map processes. If you're in that ideal, I'm sorry, it could be used to draw out those processes or like an isothermal process, right? It'd just be a constant temperature. Adiabatic means that there's no heat transfer, and so we'll get to that a little bit later. And then ideal gases are firmly in that gas region, so it's not anywhere near that that vapor dome, but you could still draw out a process for an ideal gas on a TV or PV diagram. All right, so let's go back over here. I have one. Actually, I skipped a couple, didn't I? So at a given pressure, the temperature at which the phase change occurs is the saturation temperature. I'm sorry, These should be switched, shouldn't I? There we go. At a given temperature, the pressure, so this would be the saturation pressure at that particular temperature. And so the answer for this second to last one would be the saturation temperature at that particular pressure. And as we said before, if the pressure is constant during a phase change, then the temperature is constant as well, right? And so you could see that in the upper right-hand corner for your PV diagram. If the pressure is constant, right, if you're looking straight across horizontal line, during a phase change, meaning it's underneath the dome, the temperature is constant. So that little gray dotted line is constant. Okay. All right. So those tables that we looked at, I'm going to give you a second. Come back. If I need to, at any time, if I need to stop, if you need me to stop and let you write something down, yell at me, but I'm coming right back to it. So table A2 and A3, those are only for this under the dome region. And so, like I said, at this particular pressure and temperature, you know you're saturated. But if you're not, say you're at 0.04 bar, but you're at a different temperature, that means you cannot be in the two-phase region, you could be somewhere else. And in this class, we're not really so much worried about the solid region. We don't really worry about that too much. We're really focused on the liquid and the gas region. And so our focus is going to be, all right, is it in the liquid or gas region, or is it saturated? Okay. And the rules are this right here. So if you've watched video 1.7 is really the one where you figure out, you know, it talks about how do you figure out what phase you're in, but really all of them are important. But the big takeaway message, I would encourage you to watch them so you understand why it is the way that it is. But the takeaway message is this. You have a compressed liquid if your temperature is less than the saturation temperature at a given pressure, or if your pressure is greater than the saturation pressure at a given temperature. Yeah, so you've got some things here. I won't read them because that's not useful at all. I guess we're not going to worry about the specific, let's worry about that specific volume. So haven't really talked about this guy at all as well. So let's talk about that. So your specific volume, it's the specific volume of saturated liquid at a given pressure or temperature. In other words, the saturated liquid portion of a two-phase substance. Right, so in that two-phase region, remember you've got two phases. You've got saturated liquid and you've got a saturated vapor. that V sub F is the specific volume of the saturated liquid portion of that. Your V sub G is same thing, but just for the saturated vapor, right? Or the saturated vapor portion of that two-phase mixture, because you may have some saturated liquid in there as well, right? And we're going to flip over there to our saturated tables for water, table A2 and A3, and see where you can get that information. So there we go. Here's our V sub F, and there's our V sub G. So if you have a saturated liquid, so you're right on that line right there. If you have a saturated liquid at, say, 0.04 bar, then your specific volume is going to be 1.004 times 10 to the negative 4, because, or 10 to the negative 3, because it's already been multiplied by 1,000. So when you do any calculations with that, you would say your specific volume is not 1.004, but 0.001004. So just pay attention to that. That number is actually a lot smaller than it looks right there. And on the flip side of that, if you're right here on that saturated vapor line at, say, 0.04, then your specific volume is this 34.8 meters cubed per kilogram. So let's just say, kind of going back over here, over here, I can, perfect. So let's say this is a PV diagram. So if I'm at 0.04 bar, and I mentioned if I'm right on that saturated liquid line, I have a saturated liquid. Well, this is that V sub F value. It's that 0.001004 meters cubed per kilogram. If it were a saturated vapor at 0.04 bar, then my specific volume would, my specific volume would be that 34.8 number. Meters cubed per kilogram. So just to kind of give you a representation of that. So those rules that I was mentioning before, if you're above that 34.8 meters cubed per kilogram, but you're still at that 0.04 bar, that puts you clearly on the right hand side of the dome, which would be in that superheated vapor region. If you're below, you have a specific volume below 0.001004 meters cubed per kilogram, and you're at 0.04 bar, then you know that you have a liquid, right, or a compressed liquid. All right, so these rules right here, your life will be infinitely easier if you just memorize them now. Note that the signs are different. This is a different sign from that one. But yeah, so it's just a memorization thing, right? Figuring out if you have a compressed liquid, have a superheated vapor, or if you have a mixture of both of those, right? Saturated liquid and saturated vapor, or your two-phase, right? Those last two things are the exact same thing, right? Two-phase saturated substance. All right, so problem 7, we want to know at what temperature does water condense at 30 kilopascals, and what temperature does it boil? So you've got the pressure is 30 kilopascals. I'm going to go ahead and put that in bar because we just saw that those tables are for water. Right, for water, it's in bar. So, all right. So, at what temperature does it condense and what temperature does it boil? Well, it's really asking the same thing. What we're asking for is saturation temperature. So we are asking for Tsat at 0.3 bar. And I don't really need to assume anything. It is what it is. So first place I'm going to go to my saturated tables, or my saturation tables. I can go to either, and it's saturated tables for water. We're going to repeat that over and over because right now I think for the first test, I think for the entire first test it's all water, but that won't always be the case, and so we just want to make sure that we note that the tables that we're looking at are just for water. So you can go to table A2 or A3. A2, that's organized by temperature. A3 is organized by pressure. And we don't know the temperature. We have the pressure. So I'm going to go to the one that's organized by pressure. But keep in mind, it's the same information and we could get the same answer either way. All right, so I'm going to table A3 and I'm just going to look up. Here we are. This is 0.3 bar or 30 kilopascals. And I can see the only possible temperature that I could be at and be at 0.3 0.3 bar and be saturated, i.e. going through a phase change, is 69.1 degrees Celsius. Sorry. So I can see, and I think actually, yeah, I have, if you want to write on your notes, I did clip out the section on your notes for table A3, so you can at least kind of keep yourself organized. That's what you're looking for. So 69.1 degrees Celsius. So Tsat at 0.3 bar is equal to 69.1 degrees Celsius. Sorry, so Antonio, I'm sorry I missed yours and you asked about 10 minutes ago. I wish it would ding at me. Should we have anything written if the pressure is constant during? Oh yeah, I'm sorry, you got it. I was just slow. Yeah, he was letting me know that I had skipped one of the blanks on the previous page. I'm gonna bring this over here so maybe it'll catch my eye if somebody says something. Okay, problem 8. And there is, at least for this one section, I've cut out the relevant tables so you can sort of at least highlight on it and keep yourself organized. I won't always do that going forward, but at least for Unit 1 I did while we're learning how to read these tables. So I want to know the specific volume of saturated liquid at 75 degrees Celsius. So in order to fix your substance, so to fix our, not substance, to fix the state, need 2 independent intensive properties. Right. And fixing the state is important. Figuring out what phase you're in is important because that tells you which tables to go to. So we just looked at table A2 and A3, but we also have tables for compressed water and superheated water, as we'll see shortly. So you need to know where to go. And we've got the intensive properties that we know right now is temperature, pressure, and specific volume. And so it might look just, if you're kind of trying to relate things together, you might say, well, I just know the pressure, or I just know the temperature. There's another one that we're going to talk about, and it's the quality. And that will tell us whether we have a saturated liquid or we have a saturated vapor, or a mixture of the two and the ratio of those two things. So it's still, I guess that statement is still true. It's just not as obvious that it's true, but I just wanted to, in case anybody's kind of got a question mark there. All right, but we know that it's saturated, and we also know, if I was thinking, my dome here just means that I'm right on that saturated liquid line, right? I guess that could be a TV or PV diagram, but I'm right there on the left-hand side of that line. And I'm wanting to know the specific volume. So I'm going to go to my saturated tables, organized by temperature, and that would be table A2. Okay, and just because I'm gonna put a little, I guess that kind of looks funny. There's my dome, so I know I'm right here on that left hand side. So if I'm at 75 degrees Celsius, what I'm looking for, the location, it's right there, because it's right on that saturated liquid line, right? So where the dot is the state of my substance. So if I go to table A2, so down here there's a cutout of A2. Well, at 75 degrees Celsius, there's my pressure. That's not needed, but there's my pressure, 0.3858 bar if I needed that. But what I do need is my specific volume, and it's this number right here, because the V sub F is the specific volume of the saturated liquid, right? And it's not 1.0259, it's 0.001029. Okay, let's write that. So our V sub F at 75 degrees Celsius, that's the specific volume that we're looking at for, and it's 0.0010259 meters cubed per kilogram. So I'm going to box that guy. All right. Right, so that's problem 8. And then problem 9, we want to know what the specific volume of saturated water vapor is at 10 bar. So I could draw a PV or a TV diagram, but I'm going to draw a PV one because I know the pressure. I think it'll be easier to show. So at 10 bar, what I'm looking for, well, it's saturated water vapor. Saturated water vapor. So I know that it's somewhere on this, that the right hand side of that dome. So it's going to be right there. That's the point I'm looking for. And so that is the specific volume that I'm looking at. And so when I go and look at my saturated tables, because that's where the information is going to be, because it is saturated. It's saturated vapor, but it's saturated. It's either on the dome or under the dome. But this is going to be our V sub G at 10 bar. And I'm going to be looking at table A3, that's the saturated tables that's organized by pressure. Okay, so at 10 bar, I kind of had to cut it a little bit because it was kind of long, but at 10 bar, I needed to know what temperature that substance is, that saturated vapor is. It's going to be 179.9 degrees Celsius. And then the specific volume of our saturated vapor is going to be 0.1944. So 0.1944. So 0.1944 meters cubed per kilogram. Perfect. All right. So Next guy. So problem 10, is it possible for water to boil at 0.04 bar and 35 degrees Celsius? So I want to know, can the water boil? I've put my substance, what it is in the given, and then any properties that I know about it. And so what we're really asking is, can it be two-phase, right? And we have actually go back here. We have rules to tell us whether something can be in that two-phase region, right? So if the temperature is equal to the saturation temperature at that particular pressure, or vice versa with the pressure, then we know that it's saturated. So that's what we're going to use here. Oops, I'm sorry. There we go. So what we're really asking is the saturation temperature at 0.04 bar equal to 35 degrees Celsius, or is the saturation pressure at 35 degrees Celsius, is that 0.04 bar? And you can look in either A2 or A3. It doesn't really matter. So I think I've cut I've got both kind of charts here at the very bottom here. So it looks like at 0.04 bar, the only possible temperature that you could be at, that water could be at and be in that two-phase region, is 28.96 degrees Celsius, not 35. And then if I had looked in table A2, which would have been fine too, right? It's the same information, it's just organized differently. If I had looked at 35 degrees Celsius, I'd see, well, only possible pressure that water could boil at 35 degrees Celsius is 0.05628 bar. And so I know it's not saturated. The question is, well, what is it, right? Well, I mean, we've already answered the question of the problem, but, just for, education's sake, what is the phase? So it looks like, so our temperature, just based on table A3, our temperature, the temperature of our water, it's at 35 degrees Celsius. So our temperature, 35 degrees Celsius, it's greater than the Tsat at our pressure, 0.04 bar. Right, that temperature would be 28.96 degrees Celsius. And so if you go up to those rules, it's superheated. Right? And you could do the same thing with the pressure, right? There was another rule that had something about the pressure. So our pressure, 0.04 bar, 4 bar, it's less than the saturation pressure at 35 degrees Celsius, which is 0.05628 bar. So that's another way that we could tell that it's superheated. We haven't looked at the superheated tables yet in class, so let's go look at those and see where those are. So those are actually table A4, so I just need to kind of keep on scrolling here. There we go. So table A4, this is superheated water vapor. And you can see these are actually a little bit more simple to read, because you just need to know the pressure and all of the information. It's organized in blocks of pressure, so you just need to go to the block that has your pressure on it, right? If it's compressed, you do have compressed tables. So I'm going to show you those. So this is A4, it's where you go if you have a superheated substance, and table A5, which is a little bit further down here. Table A5 is where you'd go if you have a compressed liquid. And it's organized the same way. Go to the box corresponding to your pressure and just read off the corresponding, whatever value you need, specific volume or for any of those other properties. Okay. Oh, darn it, did it again. Okay, so problem 11, and we have 5 more minutes. 5 more minutes. All right, so I do have some, you know, I kind of cut and pasted some tables here that you can use. But problem 11 is sort of, it might take us a little bit, but we want to know the phase or the phases in the system containing water at the following conditions. So we've got pressure and temperature for each of those, and then we're going to sketch it on a PV and a TV diagram showing where that dot is. Okay, so I've put everything in a given, find, assume, solution format. Notice that I've got what substance is it, and then I've got all the property data defined there. All right, so the first one is asking us what phase are we in at 10 bar and 179 degrees, 179.9 degrees Celsius. So when you solve these problems, when you try to figure out what phase you are in, so trying to determine phase, you're going to use the data in your saturated tables. So for water, if you have water, your saturation tables are A2 and A3. You're going to use the data in the saturation tables to determine, is it a liquid? Is it compressed? Or is it saturated? Or superheated? So the first place that you're going is the saturated tables, but you're not automatically assuming that it is saturated. So we'll finish just this part, and then we'll finish for today. So if I go to table A2, remember I was at 10 bar and 179.9 degrees Celsius. Well, it's not right on there, which is a little bit annoying. We haven't talked about interpolation yet, but it's kind of close, I guess. But you can kind of see, I don't know, maybe it's around 10 bar. So like I said, it's the same information table A2 as it is in A3, and sometimes one is a little bit more convenient than the other, right? Because you have a line item just for 10 bar, and you can see that yes, the saturation temperature is 179.9 degrees Celsius. So I can see that the Tsat at 10 bar is equal to my temperature, which is 179.9 degrees Celsius. So it's saturated, which means that it's either on the dome, it's on the dome, or it's underneath the dome. So if I'm going to draw it, or I'm supposed to draw a TV diagram or a PV diagram, here's my dome for the TV, here's my dome for the PV. This is 179.9 degrees Celsius. This is, say this is 10 bar. Well, all I can say is I am somewhere, actually I don't like that. Like that a little bit better. I am somewhere right there. So I can't really say with any certainty like where along that kind of highlighted line I am. But I'm somewhere on highlighted line. And I can't pinpoint it because I have more than one phase, and I only have temperature and pressure, and they are not independent in a region with more than one phase. Okay, so not really satisfying, but that is what it is. But with the next problems that we'll do on Friday, we will be able to sort of put a dot exactly where those things are. Okay. All right. So if you haven't watched those videos up to 1.7, please do make sure you do. And I will be in office hours right after this. There's a link right on the home page. Okay. All right. Y'all have a great day. Thank you. Appreciate it.
Thank you.
Thank you.